So last time we made little shapes. This is kind of what we did. I think a couple of you were absent, so pay attention to this, and maybe those of you that were here can help them out. But we made little blobby shapes like this. Please put your phones away. And we found the center of mass. Now, how do we find the center of mass? I don't think I put it in the right spot for that shape, but it's the balance point. I mean, if I took the shape and I, tried to balance it, I cut it out of the paper and I try to balance it, it'll balance at that point. And that balance point is called the center of mass. And it has a few interesting qualities to it. If I were to hang this shape from here, the string would go down, and the balance point will always be below where you're holding it if you let it swing back and forth until it settles down. Also, if you were to apply a force to this object, if that force, as long as it goes through the center of mass, the object will translate. But if you miss the center of mass and you push on it like this will translate, but it will also rotate. Okay, so if you apply a force to an extended body like this and you miss the center of mass with your force, if you extend the direction of that force out, the object's going to rotate as well as translate. But if you point your force directly into, if I cover this one up and point my force right through the center of mass, the object will, it won't be forced to spin. And we're going to talk about that force that makes things spin. We call that a torque, and we're going to talk about torque in the next unit. So, but now we want to develop a really simple equation that's going to allow us to calculate for certain very symmetrical situations or easy situations, where is the center of mass of a system? Now, if I, and that's what I'm going to show you how to do right now. Suppose I have two objects, and I'm going to say this has a mass of 1 kilogram. And this has a mass of 1 kilogram. And then I'm going to connect them with a very light rod. So, and I'm going to put my finger here, and let's say, where would it balance if I were to hold it with my finger? It's 1 kilogram here, 1 kilogram here. It's pretty easy to see where it would balance, right? Right in between them. So, and it's the balance point that we call the center of mass. So it's going to balance right here, right in between. But what if I took this rod like this, and then on this side, I put, this is 1 kilogram, but this is 3 kilograms. Make this 3 times bigger. I think if you had a little, let's say we had a rod attaching these objects, but the rod, maybe the rod weighs like 5 grams or something. It's really stiff material. It's really light. It's not going to bend or anything. And it's so light that we're going to ignore how it affects the center of mass or the balance point. So what would happen if I try to balance it right in the middle? It would tip over, wouldn't it? Gravity would pull this one down, and it would pull this one down, but this one would pull down with greater force, and so it's going to fall down. So in order for it to balance, I got to move my finger over here to the right. And I think that you know intuitively that if I put my finger right here, that it's going to balance. Does this make sense to everybody? All right, intuitive sense. Where's it going to balance? I put something heavy over here, lighter over here. You know that if you're going to pick it up, this could be like a shovel or something like that, where you've got a bigger load on this side and a lighter load on this side, so you have to pick it up. If you want it to balance, you got to pick it up right there. Well, there's an equation to figure out where this balance point is. And it's kind of like where the average mass is. So, and it's given by this equation. Let's define this to be the x direction. So where is the balance point on this x direction? Well, we need to define an origin. So where should I make the origin of the x-axis? Well, it can be anywhere you want it to be. As long as you stay with that, you'll get the right answer. So I think what I'll do is I'll make the middle of this this left side mass, I'll make that my origin. And so the center of mass is given to be m1 x1 plus m2 x2 plus dot 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 plus mn xn, and then we're going to divide by the total mass, m1 plus m2 plus dot 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 plus mn, just mn. So this is the scheme that lets us figure out where the center of mass is for this system here. Well, I need to know how far away this is. Let's say this was 1 meter away. So where would this balance point be? Well, this kind of tells us where the average mass is located. So let's go M1, that's 1 kilogram. What is X1 for this example? Well, what is the position of this little object right here if it's located at the origin? Its position is 0 meters. Plus, now let's take a look at this 3 kilogram mass. How far from the origin is it? 1 meter. And then what's the total mass? Well, we have M1 plus M2. And that's all we had for this example. We don't have an M3 or an M4 or MN or whatever. So you can stop with 2. Now, I think the most I would give you is like 3 different objects to figure out where the center of mass is. Because after a while, it's just tedious. And now you just figure it out. Well, 3 times 1, oh, that should be 1 meter. 3 times 1 meter is 3 kilogram meters. And I'm going to divide that by 3, or 1 plus 3 is 4 kilograms. And you're left with 0.75 meters. That means if let's say I had this and this on a meter stick or whatever, a massless magical meter stick, I would have to put this 3/4 the way down, 0.75 meters. And if I hold it right here at 0.75 meters, it'll balance. So that's how you figure it out for a system. Now, I can also do a system like this and get a little bit more complicated. Let's take a look at this example. So So this is going to be y, and this is going to be x, so we'll put our origin right here. Let's suppose I had a shape that looked like this. Like a sheet metal part. And let's suppose you want to know where the center of mass of this sheet metal part. Center of mass might not even be on the part. But that's okay. Let's just make this real easy. I should have made this a little bit taller. Let me make this a little bit taller so it's nice and symmetric. Well, I want to know, where does this balance, where is the center of mass along the x-axis? That is, if I go along the x-axis, where would it balance? And I also want to know, where would it balance on the y-axis? What if I was to go like this? Where would it balance along the y direction? So I'm going to make this my origin. Now let's say this is 1, 2, 3. Let's say they're centimeters. So 1, 2, 3 centimeters. And we want to know, where is the center of this part? Where would the center of mass be? And believe me, this is an important thing in engineering. They always want to know where the center of mass of their machine parts are. Okay, so in the x direction, here's what you can do. You can treat these as 1, 2, 3, 4, 5 separate masses. But if this is a sheet metal part, you can break them up into like 2 shapes, where by symmetry you know where the centers of mass are. And that's what I'm going to do. I'm going to say, let's say this is a rectangle, and this is a rectangle. Okay, now where is this? Let's do this. Let's look in the x direction. What is the mass of this part right here? I'm going to give it a mass of 2. 2 what? 2 grams, 2 kilograms, 2 metric tons? It doesn't matter, because mass is going to divide out anyway. So if this is a sheet metal part and it's just got a certain mass per unit area, I'm just going to make one up. So I'm going to say that each one of these, so the mass is just 2 kilograms. Well, we can call it 2 kilograms because people, we might be comfortable with that. So I'm going to make, and where is the center of this rectangle? It's right here. And then this, I'm going to say this has a mass of 1, 2, 3 kilograms. Now where's the center of this one? Easy, right? The center of this is right here. So now I've only got 2 objects, and it's as if I can take all the mass here and concentrate it at that one spot. And I can take all the mass over here and concentrate it at this spot. And now I can treat them as 2 particles in the x and y direction. So let's call this object 1 and this object 2. So object 1, in the x direction, where is its center of mass? It's at 1 centimeter. So, and what is its mass? It has 2 kilograms. And its center in the x direction is at 1 centimeter. And I go along the x-axis. Oh, okay, there's its center. Now, what is the mass of this shape? 1, 2, 3 kilograms. And where is its center of mass? Ooh, right there, 2.5. You see how I got 2.5? It's a rectangle, so where's the middle of a rectangle? Well, right in the middle. Now, what's the total mass? Well, this is 2 kilograms plus 3 kilograms. And notice that the kilograms cancel, so it doesn't matter that this was in kilograms, in grams or whatever. It doesn't matter. Yes? I can't hear you.
Wouldn't it be 1.5 centimeters?
Right here?
Yes.
No, it's 1, 2.5. That is its position from the origin. Yeah. Okay. Oh, it's going to be 1.5 in the y direction, as we'll see here in a minute. Now, so let's plug those values in. 2 times 1 is 2. Plus 3 times 2.5. What is that? 6, 7.5? Yeah, 7.5. That's equal to 9.5. And then we're going to divide it by 5. And that's 1.9 centimeters. So think about this. If you're going to balance this, 1.9, right about here. Doesn't that seem right? Intuitively, that it would balance right there? Yeah. And then along here, now in the y direction, let's take a look at this thing. In the y direction, the mass is again 2 kilograms. That doesn't change. But where does it balance? Ooh, 0.5 centimeters. And then the other one is a mass of 3 kilograms, but where does it balance? Now there's the 1.5 you were talking about. 1.5 centimeters. And so and then you divide that by 2 kilograms plus 3 kilograms. So 2 times 0.5 is 1, and then you have 3 times 1.5, which is 4.5, right? So that's 5.5 divided by 5. 1.1. So now think about it. If you were to balance this, wouldn't it balance right about there? Does it seem like it's right about there? Yeah, so the center of mass for this shape is not actually on the shape. The center of mass for the whole thing is in the x direction, it's at 1.9 centimeters, which is right here. And in the y direction, it's at 1.1. So the center of mass for the whole thing is right here. So it's a little bit off the part. So you can say that the location of the center of mass, I'm going to call that R, is equal to 1.9 centimeters in the x direction and 1.1 centimeters in the y direction. So there it is in rectangular coordinates. So it's actually a position. Where is the center of mass? Well, you can figure out with the x and the y. And this is kind of a big deal. What if I were to stack tiles? Like, let's say these are tiles. What if I was to put, another tile here and another tile here and another tile here? Well, that would just add, then now I would have to treat this as a third separate object, and I would have to do the problem differently. But if you just break it up into a bunch of shapes where you know where the centers are, you can figure out where the center of the whole thing is. Kind of like what we did, with this, right? I mean, we know where the centers of these, I don't know, they could be, brass balls or something. And so there we have the center here and a center here, center here, center here. Okay, and there we go. So this is kind of the basic equation that you need to calculate the center of mass in the x direction, but it also applies to the y direction. Any questions? Okay, that is all.